Do you find the idea of balancing chemical equations difficult, or do you find even the idea of what does that even mean? What does it even mean to balance chemical equations? When you are asked to do that, what do they even want you to do if you're studying in school, or if you are outside of school and have had to pick up some basic chemistry for whatever it is that you're doing in the workplace, or if you're looking at it just out of idle curiosity? So, what we're talking about today should be helpful towards you. What we are looking at is balancing chemical equations. Okay, and to start you off, we're going to ease into the idea of chemical equations, what the point of them is, and why they are useful. And once we've done that, I'll then go on to talking about the different ways that you can go about doing balancing, what balancing means, and also how to avoid some common mistakes when doing that. So if you're comfortable enough with the basics of understanding what a chemical equation is, then in that case you can probably skip ahead. I'll try to remember to leave a timestamp in the description for you to do so. But for everyone else who wants to stick around and be introduced to this gradually and understand maybe some things they may have taken for granted, I have a question, a basic question. What is a chemical reaction? What is a chemical reaction? It might be you've never actually considered the answer to that question before. But one way we can describe a chemical reaction would be a change that is happening that we can explain by events that happen at the level of atoms and molecules. So an example of this would be if you are burning coal. Burning coal is carbon. So C for carbon. That is a chemical reaction because it is a change at the atomic level. Burning carbon involves reacting carbon with oxygen. So when you actually burn coal, what you are doing is you are getting carbon and it is reacting with oxygen, O2, and that is forming carbon dioxide, CO2. So this is a chemical reaction. It is a change that is happening, and we are looking at things that are happening at the level of atoms and molecules, and that is allowing us to explain this change happening. Okay? So, one way of looking at what is a chemical reaction is by saying a chemical reaction is a change that can be explained by events that happen or events that take place even at the level of atoms and molecules. So it's looking at explaining and looking into these changes that happen by looking at the interactions between different atoms, different molecules, different compounds, okay? So essentially, when you're a chemist or a student and you're looking at chemical reactions, what you're really doing is you're trying to explain changes that are happening. And these changes can be, millions, billions of different things that, happen all around us. And what we've done here, I've just drawn an example of a chemical reaction. burning carbon or burning coal. And this right here, is actually a chemical equation. So a chemical equation is essentially a way of describing or a way of presenting a chemical reaction. So we have, what did we have? We had coal, we had carbon, and we had oxygen, and they were reacting to form carbon dioxide. And obviously, in addition to that, we also get heat as well. But that's not a chemical, but that is one of the obvious byproducts of this reaction. But when you can break this down into, there's an arrow here. So this dividing line on either side of the arrow, on this side, we have reactants. So carbon and the oxygen, they're both reactants, and on this side we have products. So in an equation, in a chemical equation, you've got the reactants on the left-hand side interact with each other in a chemical reaction, and on the right-hand side of the arrow, we have the products of the reaction. Okay? So when we say that a chemical equation should be balanced, what we mean is that all of the atoms that are in the reactants and all of the atoms that are in the products, they should add up to be the same on either side. So a balanced equation means each type of atom has the same number of itself on either side of the equation. Like here, we have, how many carbons do we have here? We have 1 carbon. How many carbons do we have here on the other side? We have 1 carbon. What about oxygen? This is an O2 molecule. So that means there are actually 2 oxygens. So O2 means it is a diatomic molecule or a dioxygen molecule. All that actually means is there are 2 oxygen atoms there as a unit. Okay? So there are 2 there. And again, this carbon dioxide molecule has 2 oxygen in it. So again, we have 2 oxygen. So this is a balanced equation. A balanced equation means that there are the same number of each type of atom on either side of the arrow. Okay, a balanced equation means that in the chemical equation, we have the same amount of atoms of each type. So in this case, we have the same amount of carbons on either side of the equation, and we have the same amount of oxygens on either side of the arrow as well. So now that we have a functional definition of a balanced equation, the same number of each type of atom on either side of the arrow in a chemical equation, we can start to look at how to go about actually doing the balancing. If you're given a chemical equation and it is not balanced, then here we are going to look at how to go about balancing that, okay? How to balance chemical equations. Okay, so I am going to give you an example. You might not be familiar with the reaction, but you do not need to be familiar with the chemistry that's going on in this example in order to understand what I'm talking about, okay? So this is the reaction of magnesium with oxygen, okay? So magnesium and oxygen can react together under the right conditions, and that makes magnesium oxide. So Mg for magnesium, Mg plus, and again we have O2, because oxygen is, remember, it's diatomic, which means molecule has two atoms in it. Di meaning two, atomic meaning atoms. Two atoms, diatomic. To magnesium oxide. Okay, that's the formula for magnesium oxide. So check, is this balanced? Count the atoms again. We have one magnesium on this side, one magnesium on this side. For oxygen, we have, again, 2, and over here we have 1. What does that mean? That means we have 2 oxygen on this side of the equation and 1 oxygen on the right-hand side of the equation. So how do we go about balancing this? Well, you go about it by increasing the amount of each of a molecule. Okay? You increase the amount of a molecule in the equation. So if I put a 2 here, what I'm saying is that on this side, there are 2 lots of magnesium oxide produced. So if I do that, then what that means is, rather than having, I will rub this out as well actually. Once I have put a 2 in front of magnesium oxide, that means we have 2 lots of everything in the molecule, which means we have 2 magnesium and also we have 2 oxygen, because there is 1 lot each, 1 atom each in 1 molecule, and we have 2 molecules in total. Okay, so we have now got the same number of oxygen on either side of the arrow, but we have only 1 magnesium on the left-hand side of the equation, but we have 2 magnesium on the right-hand side of the equation. So how can we balance that? We can balance that by putting a 2 in front of the magnesium on the reactant side, which means we need to count up again. We have 2 magnesium. So now we have the right amount of every atom. Every atom has the same number of each type on each side of the arrow. You might wonder, would it not have been easier if we look back at the original equation that I gave you, Mg plus O2 reacts to form magnesium oxide, MgO. Would it not have been easier, rather than putting a 2, so we put a 2 in front, we put a 2 in front of magnesium oxide and we put a 2 in front of magnesium, would it not have been easier to simply go and put a half? Could you not put a half in front of the oxygen molecule? Well, no. In general, you want whole numbers. So that is a point I want to make. When you are balancing equations, try to avoid fractions. We want whole numbers of molecules, because in reality you don't have half a molecule, do you? So avoid fractions of molecules. We want whole numbers. Because you can't really just get a molecule and cut it in half, can you? Because doing that is not changing the multiplicity or the amount of it present, it is literally changing what it is, okay? So that's why we've got to stay in the realm of whole numbers. So now let's look at a few more examples of equations that we can balance, and as we go through them, I'll explain the mentality that I have and the thought process I have as I go through them, okay? So we'll call this example 1. I know we've done an example above, but we'll call this example 1. E.g. 1. And that is the reaction of hydrogen with oxygen, okay? So hydrogen, you know the hydrogen atom has a symbol H, don't you? That's hydrogen, the first element on the periodic table. But as a molecule, in its molecular form, hydrogen is, like oxygen, diatomic. It has two atoms in one molecule, so it's H2. And oxygen is O2, as we remember. But do not worry about remembering things like hydrogen being H2 for the most part, because in the context of being asked to balance an equation, you'll usually be given the starting formula of all of the different reactants. You won't be expected to write them out from a word equation for the most part. But as you do more chemistry, remembering things like hydrogen is H2 as a molecule, that will start to come a lot more naturally to you, and you'll not have to worry about it so much as time goes on and as you get more experienced. So hydrogen and oxygen actually react together to form H2O, i.e. this is water. So you may have done what's called a pop test or a pop squeak test in the classroom or in the lab, which is basically you put a burning splint into a container that contains hydrogen and you hear a really loud pop. That is the reaction. So hydrogen reacting with oxygen is burning hydrogen, but the only product of it is water, which is actually fairly unique among burning things, because if you burn something like coal or oil or petrol, you always get carbon dioxide as well, don't you? Whereas there is no carbon dioxide here. So that does have some interesting consequences for if you want to consider, green fuels in the context of reducing human impact on climate change. But anyway, back to this. If we want to look at balancing this, what's the first thing we do? The first thing we do is count up how much we have of everything at the very start. Okay? H2, we have 2 hydrogen. O2, we have 2 oxygen. H2 on the other side, 2 hydrogen. O, we have 1 oxygen. So the only thing here that is out of balance is oxygen. We have too many oxygen on the left-hand side relative to the right-hand side. So if we go and we put a 2 in front of this, why am I doing that? Because we can't go half here. We can't do that, can we? So instead, we've got to compensate the opposite way by increasing the amount on the right-hand side of the equation. So once we've put a 2 there, what we actually have on the product side, we'll have to recount this, okay? So instead of having just 2 hydrogen, we have 2 lots of 2, because this is H2O, and we have 2 molecules of that. So if I was going to draw that, just as a visual aid this time, so that is 2 water molecules. And you can count, we have 4 hydrogen because we have 2 lots of 2. So we have 4H and we have 2O. So now the oxygen is balanced. What about the hydrogen? Because remember, we have increased how much hydrogen we have as well. So if you look, we have 4 hydrogen on the right hand side, but we only have 2 on the left hand side. So how do we go about fixing that? Well, if we put a 2 in front now and count again, we have 2 lots of 2, meaning we have 4 atoms of hydrogen. So is this balanced? Double check everything. 1, 2, 3, 4 hydrogen, 1, 2 oxygen, 1, 2, 3, 4 hydrogen, 1, 2 oxygen. Yep, that's balanced. So what I was doing there, basically, starting from the oxygen, if you remember at the very beginning, we didn't have enough oxygen on this side of the equation, and it was increasing here and then chasing around and chasing around. What has this changed, and how then do you correct that until you eventually end up at a balanced equation? So let's look at another example. And this example is going to be the reaction of hydrogen and nitrogen. So H2 for hydrogen, nitrogen is also diatomic, N2, and they react together to form NH3, and this is called ammonia. Okay, so again, starting point, first thing, you always have to do, first thing, is count how many of each type of atom you have on each side. So we have 1, 2, we have 2 hydrogen, 1, 2, 2 nitrogen. On the right hand side, we only have 1 nitrogen, and we also have 3 hydrogen, okay? So, what I'm going to do to start off with is we need to increase how much ammonia we are producing. We need to increase NH3. So I'm going to put a 2 in front here, okay? I'm going to put a 2 in front here, and then I'm going to recount how many of each atom we have. So 2 times 1 nitrogen per molecule gives us 2 nitrogen, and 2 lots of 3 hydrogen per molecule gives us 6. So we have 6 hydrogen and 2 nitrogen now on this side of the equation. So what I'm going to do now, we have to we've made some changes over here, and we need to chase those back across to see what is now out of balance on the left hand side and correct that. So we have 2 nitrogen, so chase this back around here. We have 2 still, so this is balanced. The nitrogen is balanced. We have 6 hydrogen, chase this across, and we only have 2 on the left hand side. So then we are going to need to change this. So we have 6 hydrogen on the right hand side, so we need 6 on the left hand side. So that's an H2 molecule, so we need 3 molecules of H2, and that is going to give us 6 hydrogen. And since there is nothing else in the H2 molecule, we've not changed the balance of anything else. We've not changed how much of anything else we have, so this is now balanced. Okay, another example. This one you can look at this one. It is the reaction of a compound called potassium chlorate. So K for potassium, chlorate is Cl for chlorine, O3. Potassium chlorate, and this breaks down to produce potassium chloride, which is potassium and a chlorine, and oxygen, which is O2. Okay, again, if you're not familiar with the reaction, don't worry about it. How many potassium do we have on either side? 1 here and 1 here. How many chlorines? 1 here, 1 here. How many oxygen? O3, so 3 here. O2, so 2 here. Okay, so this is balanced everywhere except for the oxygen. Okay? So something you could do here, if you notice something like this, you will notice then that we need to get the oxygens to balance out, but you'll also notice if I just doubled the oxygen over here, if I just doubled that to 4, that's still not going to go neatly into 3, okay? And so you'll need to think, how do I get this to balance out while still keeping a whole number of molecules? Well, one trick you can sometimes do is look for a common multiple. So we have 2 oxygens here, and we have 3 oxygens here. So if you want to find a common multiple, 3 times 2 is 6. So if we want to do something to make sure we have 6 oxygens on either side, you can then affect those changes. So how do we get to 6 oxygens? Well, in this case, on the left hand side, you would double it because we have 3. So we have 2 KClO3. That's a 3. 2 Cl plus O2, and we need 6 oxygens, remember? So put a 3 in front of the 3 O2. So now we have 6 oxygens on all sides. So count up everything again. Potassium, we have 2 potassium on this side, 1 on this side. Chlorine, we have 2 on this side, 1 on this side. Double check oxygen, O3, we have 2 lots of O3, so we have 6 on this side, 3 lots of O2 here, we have 6 on this side. So now all we need to do is balance potassium and chlorine again. So you'll notice there's 2 potassium and 2 chlorine on the left hand side and 1 of each on the right hand side. So what you can do is just stick a 2 in front of potassium chloride, okay? And then just recount, you'll have 2 of each, 2 potassium and 2 chlorine. So there we go, that is now balanced. So that's a little shortcut that can prevent you from wasting a little bit of time, but you can't always do it, okay? Or at least you can sometimes do it, but it might not be useful. Okay, one more example, and this one is the reaction of a gas called propane with oxygen. And remember, propane, you'll often get it in gas canisters. You can use it for a fuel, for things like camping stoves, that sort of thing. So this example, I think we're up to number 4 now, example 4. This is propane, and the formula for propane is C3H8. And the reaction is with oxygen plus O2, and the products are carbon dioxide, CO2, and water, H2O. Okay, once again, let's count up what we have to start with. How many carbons? 3 here. On the other side, we have 1. Okay, what's next? Hydrogen. Okay, let's count the hydrogen. We have 8 here. On the other side, we have 2. Last is oxygen. How many do we have? We have 2 here. And on this side, be careful because we actually have oxygen present in more than one of the products. We have 2 oxygen here and 1 here, which means we actually have 3 oxygen in total on the right hand side of the equation. Okay? So one tip, you should look to balance first atoms that are in multiple compounds. Okay? So you want to prioritize balancing carbon and hydrogen here over balancing oxygen. You can add oxygen later without affecting anything. So first things first, let's try and balance carbon out, okay? We have 3 carbon here and only 1 carbon here. So let me just get rid of those dots. And okay, so how are we going to balance out the carbon dioxide? Well, we have 3 carbon over here and we have 1 over here. So let's put a 3 in front of carbon dioxide, and now we have 3 carbon. So we have 3 carbons on both sides, okay? What about hydrogen now? We have 8 hydrogen here, and we have 2 here. So in water is H2O, so we have 2 lots of hydrogen per water molecule. So to get 8 of those, to get 8 hydrogen out of this, we're going to need 4 H2O. So 4 lots of water molecules, okay? So let's count up again what we end up with. 4 times 2, so 4 lots of 2. We have 8 hydrogen, okay? So we have 3 carbons on both sides, and we have 8 hydrogens, okay? So let's again tally up how much oxygen we have now. We have 3 lots of 2 oxygen in the carbon dioxide, so 3 times 2 is 6. And we also have 4 lots of 1, so we have 4 here. So 6 and 4, we actually have 10 lots of oxygen on the right hand side. So how do we get 10 on the left hand side? Well, we have 2 lots of oxygen per molecule, so 5. Let me just change the color. So 5 oxygen molecules here should give us 5 times 2 will give us 10. So this is now balanced. Okay, before we move on, what I'm going to do is show you why balancing the carbons and hydrogens here was a better idea than starting with the oxygen. Okay, so let me rewrite the original equation. We have C3H8 plus O2 reacting to give CO2 and H2O. Okay, and again, quickly count everything up again. 3 carbons, 1 carbon, 8 hydrogens, 2 hydrogens, 2 oxygens, and then we have 2 here, 1 here, 3 oxygens. So before I did tell you it was a better idea to start with the carbon and the hydrogen, because the carbon and the hydrogen are both part of a complicated molecule. Whereas if we start with the oxygen, oxygen can be isolated in balancing because it is only part of the O2 molecule here in the equation. So let me show you why it would be a bad idea to start with the oxygen. So remember, we have 2 oxygen on the left-hand side and 3 on the right-hand side. Right? How might we balance that? Well, one thing we could do, we could say, let's have 2 water molecules. And then we'll end up with, then we'll end up with 2 oxygen here, meaning we're going to have 4 in total. And we are also going to have 4 hydrogen here, remember, because just because we've put 2 in front, we don't get to only change how much oxygen we have, we also change how much hydrogen we have too. So now we have 4 oxygen on this side of the equation, and then we could then say, right, let's put a 2 in front of this, and now we have, balanced the oxygen. Except now, the rest of the equation still needs balancing. We still need to change carbons and hydrogens in order to ensure carbon and hydrogen are balanced. Okay, so then let's balance the carbon now that oxygen is supposedly balanced. So we put a 3 there. Okay, have a 3 there, so we have 3 carbons, and it also means we now have 6 oxygens here. Okay, great, we've balanced carbon. Oh, but now we've unbalanced oxygen again, haven't we? So retotaling that, we actually now have 8 oxygen in total on this side. So if you were balancing for oxygen first, then going back, how do we get 8 in total? Well, you can have 4 lots of 2, can't you? So we have 4 O2, and now we have 8. Okay, so now the carbon and the oxygen are balanced. What about hydrogen? We still need to balance hydrogen, 8 versus 4. So let's increase how much H2O we have here in order to get to 8. So 4 lots of H2O means we now have 8 hydrogens. So the hydrogen and the carbon are now balanced, but now, because of that, remember, we've also got oxygen here. So we've now changed how much oxygen we have too. So 4 lots of 1 is 4. So now we have 10 oxygen. So we are now at a very similar point to we were in the earlier example, except it's taken a lot more time to do it in. Yeah? I hope you see why, because, okay, now we have 10 oxygen, let's balance for that. Put a 5 there to get 10 oxygen. And we have 10 oxygen now. So this is now balanced. Yep. Except it took far longer and it took far more thinking than it did doing it the way around I showed initially. If you want to see again how I did it the first time round, it was by prioritizing carbon and hydrogen over oxygen, and that is because they are not present in an isolated form, they are present in a compound together, whereas oxygen was by itself. And you want to prioritize balancing for the atoms in a complicated molecule first, it will save you time. Right, one last example, and this one is a little bit harder again. So we are up to example 5 now, I believe. And this one is the reaction that a compound called ammonium nitrate, you might have heard of it, can undergo under certain conditions. Okay, so ammonium nitrate has the formula NH4NO3, and it decomposes, as in it breaks down, to produce nitrogen gas, N2, oxygen gas, O2, and water, H2O. So some things to draw your attention to here before moving on and getting on with it. The reactant actually has nitrogens in 2 different parts of it. There is a nitrogen in the NH4 group and there is a nitrogen in the NO3 group. Okay, so again, let's count up how much of each type of atom we have. We have a nitrogen here and here, so we have 2 nitrogens. We have hydrogen here, so we have 4 hydrogens. And we have 3 oxygens here, so we have 3 oxygens. What about on the other side? On the other side, we have oxygen in O2 and in H2O. So we have 3 oxygens here. That means the oxygen is actually already balanced. Okay, what about hydrogen? We have H2O, so we have 2 hydrogens. Nitrogen, we have N2, so we have 2 nitrogens. So what is out of balance? Because nitrogen is balanced and oxygen is balanced, but hydrogen is not balanced. Okay? It is this hydrogen here, which is not balanced. So we have too much hydrogen on the left-hand side relative to the right-hand side. So how can we go about balancing that? Well, let's start off by increasing how much water we have. 2 lots of H2O. So 2 lots of H2O means we have 4. 2 times 2 is 4 hydrogen, and 2 times 1 is 2 oxygen. And remember, there is also 2 oxygen here. So we've just balanced out the hydrogen, but we've also increased how much oxygen we have. So, counting up the oxygen on this side, we have 4 oxygen. Okay? So 4 oxygen, 4 hydrogen, and 2 nitrogen. We need now to balance out oxygen. So in order to do that, we are going to need to increase how much reactant we have. So 2 lots of ammonium nitrate, and let's recount everything, starting with nitrogen. We have a nitrogen here and a nitrogen here. So in each molecule we have 2 nitrogen and we have 2 molecules. So we have 2 here, 2 here, we have 4 nitrogen. For hydrogen we have 2 lots of 4, so we have 8 hydrogen. And oxygen we have 2 lots of 3, so we have 6 oxygen. Okay. Now, that means we are going to have to do some more rebalancing. And again, I'm starting with water rather than nitrogen or oxygen on the right-hand side because it contains more than one type of atom. So, rather than having 2 lots, how many hydrogen do we have on the left-hand side? We have 8. So, how do we get 8 on this side? We need 4 lots of H2O to get 8 hydrogen. So 8, 4 times 2 gives 8. We also have 4 times 1, 4 oxygens now. So let's look. We have balanced the hydrogen out. We have 8 on both sides. What about oxygen? We have 6 on the left side and 6 on the right side. What about nitrogen? Well, on the left side we have 4, and on the right side we still only have 2. So let's balance that. Putting a 2 there, we now have 4 nitrogen. So let's double check everything. Okay. Just to double check everything you've done, because in an answer that takes a while to come up with a full balanced equation for, you are prone to make some mistakes. So 2 lots of this molecule, so we have 2 nitrogens here, 2 nitrogens here, 4 nitrogen, 2 lots of 4, 8 hydrogen, 2 lots of 3, 6 oxygen. On the right hand side we have 2 lots of 2, 4 nitrogen, 1 lot of O2, 2 oxygen, 8 lots of H2, 4 lots of H2 rather, 8 hydrogen, and 4 lots of O, 4. So remember, we have oxygen present in more than one thing. So 2 plus 4, we have 6 oxygen total. So this is a balanced equation. So hopefully this was informative and helped clear up any confusion. I will look for a few resources to link down for some practice questions if you'd like to practice, but for now, let me give you a brief summary. So these are the important points to bear in mind. Do you remember what we said a balanced equation was? We said a balanced equation was an equation where we have the same number of each type of atom on both sides of the arrow in the chemical equation. Do you remember something else I pointed out that I said was important? It was, we do not like fractions of molecules when we're balancing equations. Avoid fractions of molecules, generally. They do come up from time to time in some textbooks, despite what I've told you. Okay, avoid fractions of molecules. Favor using whole numbers. And the last point, do you remember what that was? That was when you're actually balancing an equation, you want to prioritize balancing the equation using molecules that contain multiple different types of atom. So when you're balancing, prioritize molecules or substances that have, so substances containing multiple types of atom or multiple elements. Okay, hopefully you found that somewhat helpful, helped clarify some things, but like a lot of things, it might take a fair bit of practice for you to get your own head around it and be comfortable doing it. In future, I'll have a quick look at some common mistakes that are often made when people are trying to balance equations, okay? So until then, behave.